Hello. So in this video, we're going to prove Caratheodory's theorem, which is, you can call it the first step towards the constructions of measure. It is not a short proof, and it uses many tricks. I call it tricks because I'm not familiar with those, but I hopefully one day I'll be familiar with those. And then because those are not tricks, those are just observations, like really good observations. So we will, as I prove, I might need some time to retrieve my thought. So I will sometimes pause the video and go back. So let's get started. Let's first state the theorem. Okay, so Caratheodory, Caratheodory theorem. Okay. So the proof is about outer measures. So let be let be the set of all mu star measurable sets. Mu star measurable sets. Right, and then claim. Okay, the claim one is that M is a sigma algebra. And claim two is that M restricted on M is a complete sigma algebra. Complete measure. So mu star is a complete measure on M. Okay, so we're going to prove this too. And let's do the proof of claim one. So we want to show that M is a sigma algebra. So recall what is the definition for sigma algebra? Well, first of all, the empty set has to be in M. And second is X has to be in M because X here is a universal set. And then if E is in M, then EC is in M. And if I have a countable disjoint set in M, then their union is in M. So we're going to proceed in this ordering basically, but we're gonna do a little bit change because we need some pieces before proving the closure of countable unions, and I will explain more when we get there. Okay, so let's do the easy part first. So X is in M. Since X is mu star measurable. So I should remind you what does it mean by saying mu star is a set that is mu star measurable. So A is mu star measurable if for all E in X, mu star of E is equal to mu star of E intersect A plus mu star of E intersect AC. So that is the definition for mu star measurable. And then X is mu star measurable so for all E in X, mu star of E is equal to mu star of E intersect X plus mu star of E intersect the complement of X is an empty set. So E is equal to mu star of E intersect X, which is equal to this. Okay, and then similarly, we have empty set in the R for the same reason. For the same reason. Okay, suppose E is in M, then the complement of E is in M. Let's use C instead. Since mu star of E, so for all E in X, for all E in X, mu star of E, this is equal to mu star of E, let's see, intersect A plus mu star of E intersect AC. So this follows immediately from the definition of mu star measurable. And then now, so we need to show the countable. Let A1, A2 in M, then 1 to infinity of AJ is in M. So what do we mean by that? We need to show that mu star, so let me do 1, 2, 3, and 4. So mu star of E is equal to mu star of E intersect the union of AJ plus mu star of E intersect the union of AJ complement, right? So you might, so this is our goal, and then we need to show this. And you might wondering, well, how can we get there? So let's working backwards. We know that mu star, this is equal to union of E intersect AJ plus mu star intersect AC. So the intersect E intersect so intersection of E intersect AJC. And how do you get here? So notice that here we have the infinite union, which is from 1 to infinity, right? 1 to infinity. And what do we have? We have mu star of E is equal to mu star of E intersect A plus mu star of AJ. Mu star of E intersect AJC. So this is what we have currently. Okay, so and we want to show something within where inside is really an infinite union, right? So, well, the best we can do, I mean, we can do this. Intersect AJ plus mu star E intersect AJC. Right, so best thing we can do is this. However, notice that so this is equal to 1 infinity, 1 infinity. We're just unclear how to and then imagine this is larger or equal than something, right? So E intersect AJ plus mu star union E intersect AJC. It is unclear to us. I mean, what is this, right? So this, we know this is a particular larger or equal than yeah. but it's leading us nowhere. So my point is we cannot prove this directly. And that's what I mean by at the beginning, that to prove the countable closure under countable unions, we need to be clever about it. Okay, so first show A union. So if A show that M is closed under finite union. Okay, so base case, let A be in M, show that A union B is in M. So I think we're going to encounter the first trick, the first really good observation. So to show that A union B is in M, we need to show that mu star of E is equal to mu star of E union A, which is equal to mu star of E intersect A union B's content. And the previous term should be E intersect A union B. Okay, so how do we prove that? Well, we know that mu star of E is equal to mu star of E intersect A plus mu star of E intersect AC. And notice that because M is also in M, right? So M is mu measurable, and the EA, EAC, they are in, because A is in M and E is in M, so A intersect B is in M because M is, it seems like we need to show that A intersect E intersect A is in M. So my bad. So I made a mistake. So notice that definition for mu star measurable is for all E in subset of X. And since E is subset of X, A is a subset of X, or AC is a subset of X. So this is clearly a subset of X. And clearly subset of X. And therefore, by the mu star measurability of E, we have mu star E intersect A intersect B plus mu star E intersect A intersect B C plus mu star of E intersect A C intersect B plus mu star of E intersect A C intersect B C. Okay, now I'm going to draw a picture. So this is my E, this is my A, and this is my B. So, and I'm going to use green color to denote this, blue color denotes this, and a purple color to denote this, okay? So for the green color, we have E intersect B, which is here. The blue color, the region corresponds to is A intersect E intersect A, intersect BC, which is here, and the purple is here. So notice that this is equal to, or because mu star is an outer measure, right? So this is, we know the shaded region is E intersect A union B. And notice that for outer measure, we don't really have if the sets are disjoint, then the outer measure of the union of disjoint set is equal to the summation of those measure of those sets. We don't have that. We only have subactivity. So countable subactivity. So what do we have? So we have this sign. E intersect A union E plus E intersect AC intersect BC. And what does that mean? Well, so let me write it more clearly. So we have this, and the mu star of E intersect A union B is complement. So we have this. Okay. And what do we know about this? Well, E intersect A union B, union A, E intersect A union B, C, it is E, right? So, and now again, by the countable sub-additivity, we have mu star of E. No, no, no. Oh, um, so you can go this way, but yes, you can go this way. You can either think about the definition for mu star measurability. It is equal sign, but one inequality is very obvious by the countable sub-additivity, by the sub-additivity of outer measure, right? So all we need to do is we need to show the other inequality. And what is the other inequality? It's the reverse one. So is the inequality, this is larger or equal than this. So this is smaller or equal than this is obvious by the sub-additivity of outer measure. So all we need to show is we need to show this is larger than this, and we're done actually. So that is thought one, you can get your conclusion. And thought two is because of this, what is this? This is larger or equal than mu star of E because A intersect A union B is union A intersect A union B complement is equal to E. So this is larger or equal than E, mu star of E. And because this is mu star of E and this is mu star of E and they're equal, so everything in between are equal. Therefore, we have mu star of E is equal to this, or is equal to this. Therefore, which is the definition for outer measure. Hence, I'm just going to write the first one. E is, oh, I'm going to write the conclusion. So we have this, and because we have this, let's see. Okay, so that is the first, and then second, show mu star is finite additive. So what do I mean by that? I mean, if I have a disjoint A, if I have these two disjoint sets, then the outer measure of the union of two disjoint sets is equal to the outer measure of A plus the outer measure of B. We need that, okay. Second, so notice the trick we here. So I'm gonna highlight it is this is larger or equal than this. That is the trick one. And I think we're gonna use another trick. So A union B. So what do I want is I want to show mu star of A union B is equal to mu star of A plus mu star of B. Or do I need them to be disjoint? No, I don't need them to be disjoint actually. So this is our goal. Okay, so observe mu star of E is equal to mu star of E intersect A union B plus mu star of E intersect A union B C. Okay, E intersect A plus intersect AC. Okay, so no, I actually observe E is in M. E no X. This is in X. This is in X. So E intersect A union B is in X. And A is this in M. So mu star of E intersect A union B is equal to mu star of E intersect A union B intersect A plus mu star of E intersect A union B intersect AC. So this is equal to mu star of E intersect A plus mu star of E. So I have A, I have B, and this is A union B. So A union B intersect with AC. And this is E. If E overlap with B, then it is this region, right? If E does not overlap with B, then it is empty. So this is equal E intersect E. Okay, and then take E to be A union B, get mu star of A union B is equal to mu star of A plus mu star of B. And I would say this is a like really good observation that you need to run through before continuing. Okay, so final additive. And then third, so again at A1, A2 in implies we will show union of AJ 1 to infinity is in So let's just write down our goals. Notice that one is one direction. One inequality is very easy, so we just focus on proving another inequality. So this is large or equal than mu star E intersect AJ plus mu star E intersect union of AJ complement. Okay, I think we need again like an observation. Mu E is equal to mu star of E, because we proved earlier that it is closed, M is closed under finite union. So let's just do, I showed like by 2, which is the base case, but you need to show by n. So E intersect union 1 to n of AJ plus mu star of E intersect union of AJ 1 to n all the way to and the complement. And this is equal to mu star of E, mu star of union 1 to n E intersect AJ plus this. Can we keep writing this? Yes, because so I'm going to say here AJ is in M. Z is equal to 1 to infinity mu star of E intersect AJ plus, let's copy out here. Well, I think this is really intersection 1 to n AJC, and then because E intersect of this, it is equal to intersection 1 to n E intersect AJC. Okay, so what is this? This is equal to, oh, sorry, this should be n. Should be n. And notice that it is because this is large or equal than intersection of this. So what we are doing, I recall now, so you can just keep this form. So notice that this is contains E intersect union 1 to infinity AJ complement, which is equal to this plus mu star is large or equal than by the subactivity E intersect union 1 to infinity of AJ C. So we have this and this letting, so so the limit as n goes to infinity of mu star of E is large or equal than the limit as n goes to infinity of this. Okay, so this is equal to the limit as n goes to, this is equal to 1 to infinity and mu star of E intersect AJ plus mu star of E, it's copied. So we have this. And let's think about what can we do now. So this by subadditivity, mu star of countable subadditivity, because if it's finite, because it is finite, then we have I'm making video. Then we have then we will have I see. So once you have A union B, then mu star of A union B is equal to mu star of A plus mu star of B. So it doesn't really matter whether or not A union B, A and B are disjoint sets. Huh. Let me check with, hold on. I feel like that is too good to be true. Okay, yes, it's too good to be true. So I actually didn't specify there. So here, there are disjoint sets, and this, they need to be disjoint. So if you have two sets and they're disjoint, then they're union, then the inequality holds. And here, we have disjoint, okay? So, while E intersect AJ, where J equals to 1 to infinity, it is disjoint sequence. So we have union. So that's why we have this. That's why we have this equality. Okay. And here we have infinity, so we cannot do equality anymore. But we still have the subactivity, which is 1 to infinity. E intersect AJ. Okay, and the plus, what do we have on the right? So we have this. Okay. And then on the left hand side, it is just mu star of E because it does not depend on N. Right. And this is equal to mu star of E intersect the union 1 to infinity of AJ plus whatever this is. And let me think. So this is larger or equal than mu star of E, right? So hence, what do we have? We have mu star of E is equal to this, implies the countable union of AJ, where AJ are disjoint set in M, belongs to M. And then we're done with the proof showing that it's a sigma algebra. So I'm gonna highlight the part that needed really good observation. So for this line is fine. Oh, the idea of using finiteness first, I didn't come up with that. And this line is fine. What about this line? So this one is really by the second observation. Okay, and this is a good observation. So we have this inequality, and then taking the limit. So I would say this is also a good observation. I think you can get it by yourself. Right. Okay. So now we already showed the first claim, right? We finished the first claim. And then we need to show that mu star is complete measure on M. So claim 2, proof. So first of all, we need to show that mu star is a measure on M. And second of all, it is a complete measure on M. Okay, so since mu star, so since mu star is, okay, let me start from the beginning of the definition of measure. So mu star of empty set. Well, the definition for mu star is the infimum, right? It is equal to the infimum summation 1 to infinity. The definition here is rho. Rho of EJ, where EJ is in M, and the empty set is a subset of union of EJ 1 to infinity. So consider, so this is going to be smaller equal than one of the elements in this collection, right? So what could be one of the, since empty set is in empty set is in algebra, so 1 to infinity row of empty set, row of EJ, where EJ is equals to the empty set is in M, which is equal to 0. And because the outer measure is non-active, so therefore mu star of empty set is equal to 0. And then let E1, E2 in M, and we want to show what? We want to show that mu star of the union of EJ, again, let's use A instead. So A1, A2, union of AJ is equal to mu star summation of AJ. So we want to show this. And how do we show this? A1, A2, mu star is a union of AJ, mu star is equal to summation of AJ. So how do we show that? How do we show this? Okay, so I think one inclusion, one inequality is obvious, right? So our goal is to show rather inequality. Okay. So that is our goal, and I think we will use definition for mu star, which is infimum. Okay, so again, observation, if mu star of the set is equal to infinity, then we are done. I'm gonna highlight because this appears in many proofs. So suppose mu star of union 1 to infinity aj is finite. Then by the definition of mu star, for all epsilon larger than 0, there exists a collection. What is that collection? There exists a collection of E k is equal to 1 to infinity in such that the union of 1 to infinity of aj is union of 1 to infinity of ek. And because this is infimum, so summation 1 to infinity rho of ek is going to be smaller or equal than mu star of union 1 to infinity of aj plus epsilon. And then let's use this in the way that is useful for us, which is this is larger or equal than 1 to infinity rho of ek plus epsilon. Okay, I think at some point we need to use something over here. Let me double check. Sorry, it's my bad. I used a different observation that is not very useful for this proof. So our goal is still to show this inequality, and then this is still true. If it's infinity, then we're done. And so this is our going to suppose this, okay? Actually, this is a little bit different. So here we can actually use our previous result to show this equality holds. So let's get rid of the, sorry about that. So let's write down this, what this is, right? So I feel like once you have equality, my instinct was to prove the equality right away, but sometimes it's easier to prove inequality separately. But here, I guess, because we proved something before, we can use that. So this is equal to mu star of, because this is in M, so we know this is mu star measurable. So we have this is equal to because this is in E, so no, this is aj is a subset of X. And we know that aj is M star measurable, so we treat this as the set E quotation mark. Okay, so 1 to infinity of aj intersect aj plus same thing intersect ajc, so that give us mu star of aj. Let's refer to the previous one. The limits. So we have this. Hmm. E intersect AJ plus okay, so we could use something maybe use this. So let me write this as I don't know, 1. So here this is the E in the above equality. So what do we have? We have from E we have, let me just write down that first. So it is equal to 1 to infinity mu star AJ intersect AJ plus mu star union 1 to infinity AJ intersect with the union 1 to infinity of AJ JC. Okay, this is definitely something I didn't thought about. So this is by 1. So we have this equality. And notice what is this? This is 0. So 1 to infinity mu star union 1 to infinity AJ intersect AJ, which is equal to 1 to infinity mu star of AJ. And therefore mu star is a measure. I guess from here we can, if we don't want to use A, if you want to follow more intuitively, I think we can actually like prove by ourselves. Basically, you're proving everything all over again. So here your E is a union of AJ and E intersect the finite, which is equal to this. And then you by using the finiteness, you have this, right? And once you have the finiteness, you take the limit, and then you got this, and you got this. So this is what we want. So it's really, so while you're proving this is larger than this, you are potentially proving this is larger than this. And because at the end is mu star E, so everything's equal. So I'm gonna label this 1, this is 2, and then I think we used by 2. Okay, and then that finished, then mu star is a measure. And so next, prove, so prove that mu star is complete measure. How do we prove completeness? Well, recall that usually if I give you a measure and I want to tell you, okay, I tell you this is a measure and I want you to prove the completeness of this measure, what you do first is you pick up a new set of this measure, mu measurable new set, and then you pick a subset of that new set and you show that the subset, any subset of this new set is also measurable and the measure is equal to 0. For here, it is the same, but a little bit different. So say we have E that is a new set, because we already showed that new star is a measure. So for example, we pick E and E mu star of E is equal to 0, right? And then we pick a subset of E, which is B, which is a subset of E. And so our goal is to show that mu star of E is equal to 0, right? But we know that actually mu star has domain power set. So in order to write mu star of B, you don't need to prove that B is mu star measurable. So you can directly use mu star of B because that makes sense. And the reason that makes sense is mu star has domain power set. And the B is a subset of E. So B is definitely a subset of the universal set X. So you want to show that mu star of B let me think. You want to show that B is also mu star measurable and the measure of B is equal to 0. So it is equivalent as proving that because you have mu star of B smaller equal than mu star of E, where mu star of E is equal to 0, so you have mu star of B is smaller than 0, which means mu star of B is equal to 0, right? So you have that. And all you need to show is that B is actually mu star measurable. And that is equivalent to prove. So given that mu star of B is 0, you want to show that B is mu star measurable. And why don't you show for every mu measurable set, mu star of that measurable set is equal to 0. Now, as I am thinking, I feel like those two are different statements because you're given a new set and you're trying to show that the set B is measurable. B is measurable, which is a necessary condition. Let me think about this. So it is a little bit different, and I'm sorry if I confuse you. So we need to show that mu star is complete, right? And what does it mean by complete? Well, it's actually equivalent as showing for all A in the power set such that mu star of A is equal to 0. Then A is mu star measurable. Now, why that is true? Let's see how that aligns with our original strategy to prove a measure is complete. So a measure is complete even only if, given that if we have E such that mu star of E is equal to 0, then for any A that is subset of E, mu star of A should be equal to 0, right? Well, so we need to show this, right? This is our goal. And we're wondering if I have shown this, how does that help us to directly conclude this is true? This is true. So if you have mu star of E is equal to 0, the mu star of A sorry, so if for all A mu star, sorry, let me start over again. So for all A in this mu star of E is mu star of A is equal to 0, then A is mu star measurable. So original strategy is that pick E in M such that mu star of E is equal to 0. Show for any A that is subset of E, mu star of A is equal to 0, right? So connection. Well, if so pick E such that the mu star measure of E is equal to 0, and then pick A that is a subset of E by subadditivity. No, not by subadditivity, by like monotonicity. Tonicity mu star of A is equal to 0. So we show that mu star of A is 0. Of course, A is in the power set, right? So oh, actually, I did it wrong. So original strategy here is pick E in M such that mu star of E is equal to 0. And we need to show that for all subset of E, A is in M. Right. So, and then the connection, now I'm clear. So connection is that pick E in M such that this is 0, which means that E is a null set with respect to the measure mu star. And then we pick A, which is a subset of E. And then by monotonicity, we have mu star of A is equal to 0. And of course, A is in PX, right? So, so by A, by 3, so because mu star A is equal to 0 and mu is a subset of X, which is an element of power set of X. So by 3, A is in M. And then we're done. Thus, it only remains to show that to show this, which is 3, right? So how to show this? So if I have a mu star of A, well, first off, I don't really know if A is in M, so I just assume that A is in PX. So A is in PX. Okay. So this is to show mu star for all E in X. Mu star of E is equal to mu star of E intersect A plus mu star of E intersect AC, right? And then, well, we already know that by subadditivity, this is equal to 0. By monotonicity, this is equal to 0. So we just need to show that this is equal to mu star E intersect AC. Okay, so let's try. So mu star of E is W larger or equal than mu star of E intersect AC by monotonicity, which is equal to mu star of E intersect A C plus mu star of E intersect A, right, which is E larger or equal than mu star of E. And because I have this on the two ends, so everything is equal. So therefore mu star of E is equal to mu star of AC, and we have this. And then therefore we're done. Mu star is indeed complete measure, and of course by monotonicity of also measure mu star of A is equal to 0.